Hey, how's it going, you guys? How you guys doing? Everybody good? All right. You guys have any questions? I'm here a little early. Everybody good? All right. We'll get some more in here. If you guys do have any questions, let me know. Homework is up on Webassign, but I would look at the worksheets first for Trig sub. We're going to do one more day of Trig sub, and then we're going to move into the next topic. And then you guys have a test next Thursday. Probably say this again here in a few minutes, just so it's on the recording later.
It says you're recording now.
It is recording now. I don't usually post this like beginning part because on the recording it just shows up as a black screen.
Oh, okay. Are you kind of still required to record it though?
I'm not, but I leave it recorded so I don't forget to start it.
Okay, that's fair.
Yeah. Yeah. So we don't have to record anything, but I feel like it's better. Yeah, I guess we need a lecture of some sort. So this is the lecture that we get. So I do record that. But do you guys think it's, I mean, you're here, so obviously I guess you think it's better to come live?
Yeah, 100%.
Yeah, agreed.
I missed a couple of days and it took me forever to catch up on the videos.
Okay,
Yep.
yeah. Like I think it's just harder. Next semester, like I have fought a lot with some people at the college about not having a synchronous time. And so I've really pushed to have a time where, we meet Monday, Wednesday, Friday at 11:30 or whatever. So like too late for you guys, but we'll have a set class time for Calc 2 in the spring, even if it's online, which I think is better.
Hopefully it'd be in person.
Yeah, I mean, it'd be better if it's in person, if it's safe, but I much prefer to be in person. I don't prefer to catch COVID, so I think I will.
Yeah, that's fair enough.
Yeah, I think I will stay online if I don't think it's safe. But yeah, I mean, I would much rather be teaching you guys in person if it was safe. So, but I think it works okay on here. Like, I don't think it's as good as it would be if it was in person, but I think it's working. You guys seem to be doing okay overall, right? And all right.
First exam didn't go so hot.
Did it not? Okay. If it didn't, guys, you should stay and we should go over the test and, stay after class. Wednesday's a good day. Monday, Wednesday are the good days for that. Tuesday, Thursday is hard for me to stay after because I teach again within like a half hour of this. But Monday, Wednesday, I can stay after usually. Although now we should probably be working on next week's test rather than last time. All right, let me start sharing the screen and we'll get started on this. So, okay, and you know what? We're just gonna leave it like this. Okay, so last time we were going through trigonometric substitution, and I wanted to do, we're not going to do a ton more with it. We've kind of been through what we're going to do with that. But I wanted to go through one more example completely all the way through. And we're actually going to go through two. But this one is pretty challenging. We're going to work on it. And then we're going to go through one and explain why what we're doing is allowed. So we didn't really talk about some of the assumptions we were making yesterday. And so it turns out that everything we were doing is legitimate, but we haven't talked about why that's fair and what even the issues are. And so we'll talk about that on the next example. The other thing I wanted to talk briefly about is how to tell when it's trig substitution. So usually trig substitution problems involve a square root. They don't have to. So trig sub can be used anytime you can simplify the expression by using trig. You'll see an example or two on the homework where you don't have a square root. One of them has a 3/2 power, and that basically is a square root because of the 3/2 power. But then one of them doesn't have a square root at all. And so you'll see that, and I think that problem actually tells you to use trig sub. But on the Webassign, there's one mixed in where, hey, it happens to work to use trig sub to get that problem to work out, and there's not really a better technique for that problem. And so you'll see that on the homework, but most of the time it involves a square root. And then the other options aren't really good options. So like if you look at this problem, the first thing you really should be, the first legitimate effort you should be making is probably U sub. And so you should try to mess with U sub, at least in your head for a little bit. And it doesn't work. So there aren't good U substitution techniques that'll work on this problem. There are some on some of the other trig sub problems. So you'll see again on the homework, you'll see one mixed in for sure where you should use U sub and not trig sub. So kind of watch for that. And then there may be some other ones where you could be creative with U sub and get them to work. There are definitely problems where you cannot. And so trig sub is a legitimate option and it's something we should think about. But when you're looking at these problems, typically there's no overlap between these and parts. So like it would have to be really, really creative to get parts to work to on a problem like this. So the decision is really down to, does U sub work? And if not, let's try trig sub. And so when you're looking at this, U sub does not work. So then we're going to try trig sub. And then, so that's kind of the thought process. Again, there are no hard rules as far as when you use trig sub and when you don't. But that's kind of the basic idea that if U sub isn't going to work and you do have the square root, then trig sub is something worth trying. And so we're going to do that here. And let's go through it just to get kind of practice doing this one more time. Then we're going to go through one similar to yesterday and then talk about the theory behind this. But when we do this problem, once we determine that we're going to try to do trig sub, remember that you have to pick x, and you have to pick a coefficient for x, and you have to pick a trig function for x. And kind of you should think through both of those separately. So what coefficient should I pick here? Should I pick 3/2? Should I pick 2/3, 4/9, 9/4, something else completely? What's the good option here? And I don't have chat pulled up, so if you're saying it in chat, let me pull that up. Okay, nobody's saying it in chat either. So all right, yeah. So somebody says 2/3. So 2/3 is the right option. 2/3 is good because, and I think the easiest way to think of it is when you're looking at the part where you're going to use the trig sub, you end up using it on all of it, but mainly the square root. You're subbing in for x. So by subbing in for x, you're able to change the coefficient that's on the x, and you're not able to change this one, but you want to match that one. And so you want to cancel the 9. The way you do that is you put a 3 on the bottom because you're going to square it first. And then you want to end up with 4. And so you put a 2 on the top so that once you square it, you end up with 4. So we're going to pick 2/3. And now you have to pick a trig function. And the 3 options that we're going to use are sine, tangent, and secant. What option works here? Remember, based on what we were doing yesterday?
Secant.
Secant, yeah. And that works because of a manipulation of the identity 1 plus tangent squared is secant squared. So secant squared of theta minus 1 becomes tangent squared theta. And so the idea is when you're picking that trig function, you want to end up with another perfect square trig function, and you want it to be positive. So secant squared minus 1 is positive tangent squared. The other trig functions, or at least sine and tangent, those cannot be manipulated to get a positive trig function squared like this. And so we want to use secant. Okay, once you find x, you then, or once you figure out what x is going to be, you find dx based on that. So dx is the derivative of x times d theta. And so the derivative of 2/3 secant theta is 2/3 secant theta tangent theta. And so then dx is 2/3 secant theta tangent theta d theta. Any questions on that? So please ask if any of this is unclear. Like I said, we're not going to do a ton more with trig sub, but you do need to be able to do this for next week's test, but hopefully before that. All right, we're good? Okay, so then what I would recommend is that you go to the side somewhere and deal with the square root part. So we've got 9x squared minus 4 in the square root. We're going to sub in the x. So we get 9 times 2/3 secant theta squared minus 4. I'm going to skip a little bit of this, but when we square this, we get 4/9. And so let's make that a little more legible. That should be a 2 there. So 2/3. So when we square the 3, the 9 cancels and we get 4 secant squared theta minus 4. The 4 then factors out. Secant squared theta minus 1 is tangent squared theta, which was the whole point. And then the square root of 4 tangent squared theta is 2 tangent theta. So when we go to the original problem, the square root gets replaced with 2 tangent theta. The x outside of the square root, if there are any, they're not always any, there aren't always those, but if there are some, x cubed here, we replace that with 2 to the 3rd over 3 to the 3rd, so 8/27, secant to the 3rd theta. And then remember that we need to replace dx. So we put 2/3 secant theta tangent theta d theta in place of dx. Okay. Any questions to there? All good. All right, so now we're going to simplify that down. And to do that, we factor all of the coefficients out. So the 2 on top stays as a 2. The 8/27 flips and becomes 27/8. And the 2/3, because it's not in the bottom of the fraction, does not flip over. So we pull out the 2, we pull out 8 over 27, but it's the reciprocal of that. And then we pull out the 2/3 as it is. And now we cancel stuff out, so we can cancel one of the secants. If we do that, we end up with 2 tangents on top and 2 secants on bottom. All right. Any questions to there? Okay, so if you go back and look at kind of what we were saying yesterday, we were talking about 3 broad steps for trig sub. All of this stuff that we've done to this stage is basically the first big step. So you pick x, you find dx, you deal with the square root if there is one, which there usually is, you plug everything in and you simplify it down. And all of that, if you look at the examples from yesterday and then any of the homework problems, all of that is pretty much the same on every single problem. So even though it's very involved, what you're doing is pretty routine, which is not true for like U sub and the more complicated integration by parts. It's different from problem to problem because you have to be pretty creative on some of those harder problems. But here you're doing pretty much the same thing every time. And now once you're to here, this is where it can be a little different because you have this trig integral. And so this could be a basic form. This could be powers of sine and cosine, like I think we did one yesterday like that. Could be powers of secant and tangent, what this sort of is, but the fraction makes it a little different from the standard ones we did. So it could be a lot of different things at this stage. And so the second big step is, okay, whatever this is in terms of trig, we got to figure out how to do it. And so there probably is more than one way to do this one. Does anybody have a good idea as far as what we might do here? It's tricky.
Can you move tangent out of the fraction and then change secant into, or 1 over secant to cosine?
Yeah, so, okay, so what I think you're saying is that you can rewrite this as tangent squared. So I'm just writing it to make sure I'm getting what you're saying. I think you're saying this, is that right? And then 1 over secant squared is cosine squared?
Yep, and then rewrite tangent.
Okay, that's a real good idea. So let's go with that. Actually, we'll just do that on the side. How do you rewrite tangent? You're right.
That'd be sine squared theta over cosine squared theta.
Yeah. So that's probably the first thing I would write within the integral is that step. You write as much of that as you want to, but tangent squared is sine squared over cosine squared. And then the secant squared in the bottom, you can flip it and make it cosine squared over 1, or just cosine squared, which is exactly what Jordan was just saying. That's exactly right. I think it's the most efficient way to do the integral because of what now happens. There are other ways you can get to the same answer, but I think this is the best way to do the problem. I think it's the easiest. Let's simplify down these fractions. So out here, the 3 cancels with the 27. So we get a 9 up here. The 2 cancels with the 8 and we get a 4. And then this 4 cancels with this 2 and we get a 2. So we get 9 halves when we break that fraction down. So Jordan's right about how to handle this. Why is that a good idea? What should I now do with that integral?
You can cancel out the cosines.
Yeah, let's cancel out the cosines. And so we get 9 halves integral sine squared theta d theta, which is not a basic form, but what can you do with that, or what should you do with that to deal with the integral?
U substitution.
U substitution, but after using what identities? Or what identity? So it's like an even power of sine.
Half angle formula.
Half angle formula. So the half angle formula for sine is that it's 1/2 integral. The half angle formula doesn't include the integral, but the half angle formula says it's 1/2 times 1 minus cosine of 2 theta d theta. And so we get it to there. Does that make sense to everybody, what we're doing? Okay, any questions so far? Okay, so the coefficient in front is 9/4, and it carries to both parts. We're going to split this integral up. And so we're going to get 9/4 integral 1 d theta minus 9/4 integral cosine of 2 theta d theta. The integral of 1 d theta is theta. And the integral of cosine 2 theta is 1/2 sine 2 theta. Technically, there's like a quick u substitution there, but we get it to that point. Does that make sense to everybody? Any questions to there? Okay, so now that middle part, this is harder than the ones we were doing yesterday. The first one was real straightforward. The second one was a little bit tougher. This one's probably the hardest of the ones we've done, but this is the part that's different every time. So this is where you do the trig integral, however you do the trig integral. You may have to be a little bit creative with identities like we did here. You may have to use u sub. Rarely, you may have to use parts, but you do this trig integral. And so then you get this answer in terms of theta. And so we kind of went through 3 cases yesterday. I don't think we outlined those specifically, but we went through 3 different things that can happen in the answer. And there are more things that can happen in the answer, but there are 3 things that are real consistent in these practice problems. One is you can have theta not in a trig function like this. Another is that you can have just theta in a trig function, which we don't have here yet. And then another is that you can have 2 theta inside a trig function. In general, you can have other stuff, but those are probably the most common things that you're going to see. When you have 2 theta in a trig function, you want to rewrite it so that it's just theta inside a trig function. So we're going to use the double angle formula for sine 2 theta, or the double angle formula for sine. And what the double angle formula says is that sine of 2 theta is 2 sine theta cosine theta. And you don't have to do that all the time, but you do that here because we're going to try to go from theta back to x using a diagram. And the diagram works well for theta, but does not work well for 2 theta. Does that make sense to everybody so far? Good. Okay, so now we're going to draw a diagram, and the way we do that is we go back to the original substitution. So we come over here, and the original substitution is that x is equal to 2/3 secant theta. And we're going to solve that for the trig function. So secant theta is 3x over 2. And now we're going to label a triangle in the first quadrant based on that. And so we assume theta is an angle in the first quadrant. Secant is the reciprocal of cosine. So secant is hypotenuse over adjacent, or r over x. If you think of it as hypotenuse over adjacent, here's the hypotenuse as 3x. Here's the adjacent side as 2. Or you can think of it in terms of like the more formal definitions where it's r over x. And so r we label as 3x and x we label as 2. However, you've learned trig, you can do it either way, but you get the same thing. And then the third side we find by doing the Pythagorean theorem. So we take the square root of this squared minus this squared. So we get the square root of 9x squared minus 4 here. Does that make sense to everybody? Any questions? Okay, so now theta we get by using inverse trig. So when theta is not in a trig function, we want to go to this equation where we've solved for secant theta, and we say, okay, theta is the inverse secant of 3x over 2. It's the inverse whatever of this. So if this was sine, it'd be inverse sine. If this was tangent, it'd be inverse tangent. Since it's secant, it's inverse secant. So everybody follow that? Okay, and now here, the 1/2 and the 2 cancel, so we're going to get just 9/4. And then sine theta, we read from the diagram. Sine theta is the square root of 9x squared minus 4 over 3x, because sine is y over r, or opposite over adjacent. Canceled those. Cosine is it's opposite over hypotenuse, or y over r. Either way, it's this. And then cosine is adjacent over hypotenuse, or x over r. And so it's 2 over 3x. And now we're going to cancel some things out. And so we get 2 canceling with 4, where that's a 2. The 2 3s cancel with this 9. And then that's about all we can do to simplify this. And so we get 9/4 inverse secant of 3x over 2 minus the square root of 9x squared minus 4 over 2x squared. And this ended up being similar to the one we did yesterday, but the internals of this were a little different. Okay, and so that's the simplest form of the answer. Any questions on that? Everybody good?
Didn't you say something about how that unknown side of the triangle isn't always going to be like the original thing in the problem?
It is going to be that, as long as there was a square root in the problem to begin with. So
Okay, okay.
this square root will always match that. But what I think I did say is that you should not assume that you have that. Like, you should solve it, and then if you don't get the same square root, that's a flag that you're probably doing something wrong. You know what I mean? I think what I probably said, James, is that not that it won't match, but if somehow yours doesn't, then you need to go back and check what you're doing.
All right.
Does that make sense? Okay. Other questions?
Yeah, what's the purpose of converting it from theta to x? Like, what does that do, really? Like, what's the purpose?
Okay, look, Dominic, if you look at this problem, like, I know there's a ton going on, but what the problem's basically saying is find a function whose derivative is this. So if I take its derivative, I need to get this as the answer. Well, if you put this as the answer, the derivative of that is not this. You know what I'm saying? So, like, we made up theta. And so you have to go back to x, just like on a u sub problem, you have to go back to x from u. It's just easier on a u sub problem because when you set it up, it's u equals something. And here, when we're doing theta, it's not theta equals, it's x equals. And so you're kind of doing it backward. Does that make sense?
Yeah, that makes sense. Thank you.
Yeah, no problem. And everybody loves trig, which makes this even more fun, right? So, sorry, I know this is not the easiest method. Once you do get this down, and I know this doesn't sound like I'm telling the truth, it sounds like I'm just trying to make you feel better, and I'm really not. Once you get this down, you do have to practice this, but most people by the end of this end up thinking these are not as bad as the harder U sub and the harder parts we were doing last week because there's less creativity. So, like, it is a lot on each problem, but like the beginning of the problem until about here, that's always the same. And then this end stuff, yeah, the diagram and stuff is a lot to deal with, but once you get used to doing this, this is the same every time too. And so the only place where there's any creativity is this trig part, which granted is not much fun, but like, if you can get this integral, the rest of it, once you've done a few, you're doing the same thing every time, which is not true for the harder U sub, and it's not true for the harder part. You have to be pretty creative on those, and on these you don't. It's just a lot to do. But once you get it, it's really not that bad. You do have to practice though. All right, other questions so far? Other questions? You can put them in the chat if you don't want to unmute yourself, but we do want to make sure we've got this. Okay, so I want to go through, if there are any questions, please ask. It's fine. Thought I heard somebody. Okay, maybe not. All right, so I want to go through this one pretty fast. It's very, very similar to the one we did yesterday. And the point of this is not that we need another example. It's that I want to talk about the assumptions we're making here that really are kind of questionable. And so let's go through it pretty fast. The trig sub we should make here is x equals 3 sine of theta. And then that means dx is 3 cosine theta d theta. And now I'm going to go down to the side and rewrite the square root and plug everything in. So we get 9 minus 3 cosine theta squared. And then that's 9 minus 9 cosine squared theta. You factor the 9 out.
Shouldn't it be sine?
Yep. Please don't randomly change it. Thank you. So this is sine. My fault, you guys. All right, so 3 sine of theta, sine squared theta here, sine squared theta here, and now 9 cosine squared. Thank you very much for telling me that. And then the square root of that is now 3 cosine theta. All right, so I want to go fast, but not so fast that we're doing the problem wrong. All right, everybody good to hear? Sorry about that. All right, so dx is 3 cosine theta d theta, so we're going to replace the top with that. The x squared on bottom becomes 9 sine squared theta, and then the square root gets replaced with 3 cosine theta. All right, so we factor out all of the coefficients, so we get 3 times 1/9. Let's do that underneath. Some space later. So we got 3 times 1/9 times 1/3. And then in the integral, we get 1 over sine squared theta d theta. Take one more step to simplify that. Actually, we won't. We'll talk about that in a second. All right. Questions to there. I want to make sure we're good. I know I'm going fast. All right. So there's a little less going on this one, but it is basically the same thing as what we did on the beginning of the last problem. So you pick x, you find dx, you get rid of the square root, you plug all the stuff in, and now you simplify it down. And now we have this trig integral to deal with. On this one, the best approach is to rewrite this as cosecant squared. And so we can cancel the 3 and the 1/3 and get 1/9. And now we've got the integral of cosecant squared theta d theta. The antiderivative of that is negative cotangent theta. And so we get it to there. And so this middle part's a lot easier than the last problem, but that's the part where it does change from one problem to the next. Everybody good to hear? Okay, and now we're going to draw the triangle. We're going to say, okay, x is 3 sine theta. So sine theta is x over 3. We assume that we're in the first quadrant, so we draw an angle here. And then this is theta. So we labeled this side as x and this side as 3 because sine is y over r, or opposite over hypotenuse. That gets us the third side as square root of 9 minus x squared by using the Pythagorean theorem. Does that make sense to everybody? Okay, cotangent is the reciprocal of tangent. So it's x over y or adjacent over opposite. And so the adjacent side is the square root of 9 minus x squared. The opposite side is x. or the x side is square root of 9 minus x squared, and the y side is x. And so then you simplify this down to negative square root 9 minus x squared over 9x plus c, and now that's the answer. Okay. Any questions on what we're doing on each step there? Okay, I want to talk real quick before we get to the theory about the other stuff that can happen in the answer. So I was kind of saying there's 3 cases that come up quite a bit. Not every time do these happen, but here they didn't. Only this one case happened. And then there are other things that could happen. But the other main things that tend to happen are you could have like or you can have theta not in a trig function, and then you can have 2 theta in a trig function. And so this purple is not part of this problem, but that's like, okay, if in this answer you had gotten these, the way we do this is we say, okay, that's 6 theta minus 4 times 2 sine theta cosine theta because of the 2 theta inside. And so you rewrite it using just theta using the double angle formula. For theta outside of a trig function, we use inverse trig. So it would be inverse sine x, and then sine you get from the picture, sine theta is x over 3, cosine theta is square root 9 minus x squared over 3, just as a quick review of, okay, these are the 3 main things that tend to happen. You have a trig function with just theta, you have theta not in a trig function, and then you have 2 theta in a trig function. In general, other things could happen, but these are the things we typically see on the practice problems we will end up doing. And so that's how you would deal with that in the same scenario. But again, this is not part of this answer. All right, does everybody follow that? Any questions so far? Okay, so what I want to talk about, and this part, it's completely your call, especially in a remote class, how you want to take notes and stuff. But what I would recommend is that you kind of just listen and think about what we're talking about, because it's weird and it's a lot of trig theory. And so I do want you to understand this. So let's think about what we're doing. But this is kind of, let's see why all this works and what are the issues with what we're doing here. So there are several places that I'm going to label in red where we're kind of cheating when we do this problem. And by cheating, I mean, we haven't really talked about why what we're doing is okay. And the first place where that happens is right here, where we let x equal 3 sine theta. So we've been doing that now for the past couple of lectures, and we've never said why that's okay or what might be wrong with that. So one thing that is wrong with that is that sine theta is very restrictive on what sine theta can actually be. So like sine theta can never be like, for instance, 12, right? Like you never take sine of an angle and get 12 as the answer. What's the biggest thing you can ever get for sine theta?
1.
1. And what's the smallest thing you can ever get for sine theta?
-1.
-1. And so we are assuming that it's okay to just say, okay, well now this is between 1 and -1. So that restricts x a lot. And that in general is not true. X could be anything. And so this part, we kind of cheat here and just say, okay, well, we're going to put this weird restriction on x and hope we're all right. And we've not talked yet about why that's okay. And that's the kind of thing I want to talk about. So that's the first place. The second place is down here. 2 lectures ago, we talked about where really this should be the absolute value of cosine, because we don't know whether it's positive or negative. And so we talked about how the square root always is positive, and really you should have an absolute value there. And so we're cheating by not putting the absolute value. And the main reason we're cheating and not putting the absolute value is because what would we do with that up here? And so we need to talk about, is that okay? And if it is, then okay, why are we able to continue that? And so we cheat there. And then the next spot we kind of cheat is over here with this diagram. so we're assuming theta is in the first quadrant, and we never have said that. So like, what if theta is actually over here? Or what if it's in the third quadrant? Or what if it's in the fourth quadrant? And so is it okay to just use this diagram and get all the answers that way? And so that's a issue. And then the last spot is not something we did in this problem. If this diagram's right, this is right. But if that diagram's right, this might not be right. So theta becoming inverse sine, which we don't do on this problem, but we have on a couple other problems. We're cheating there because if you remember back to trig, and it may have been a while and we may not remember, but when you're talking about inverse trig, there's a domain restriction that goes with sine that we've not talked about. And so this imposes an additional restriction that theta may or may not have. And so if you go back up and look at all the places that I've marked where we're cheating, it's basically every part of the actual trig sub. Everything else we do in this is stuff that we already knew how to do, but everything new that we've put in for the past 2 days, all of that is questionable at best, and we've not talked about why it's okay. So these are the main steps, like our original thing, the way we get rid of the square root, which is the whole point, the diagram which we use to go back to x, that's questionable. And then when we're dealing with theta not in a trig function, that's questionable as well. And so let's go through and talk about why it turns out all of this is okay. Hopefully it is. We've talked about it now for the past 2.5 lectures. So, okay, up here, the big issue is that sine theta is between -1 and 1. And so that means that we're then getting that x is, in this problem, x is between what and what, according to this. If sine is never bigger than 1, then x could never be bigger than what here? What do you guys think?
3.
3. Yeah. So that means that x, and this is the actual symbol, not the arrow, x is between -3 and 3. Normally, that's not allowed at all. Like, x could be anything you want. What about this problem, though, means that actually this is true? Why, even though we've never said it, why does this problem imply that x has to be between 3 and -3? There's something in there.
Because of the square root?
Because of the square root, which is basically in all trig subproblems. And so because of this square root, x can't be bigger than 3, because if it were, you'd have a negative under the square root. It also can't be smaller than -3, because if it were, you'd get a negative. So like 9 minus -4 squared, that's negative. You can't do that. And so this assumption's already there, even though we've never said it. And so we're not imposing an additional restriction. When we're doing tangent, who remembers, so like sine, the range is -1 to 1. When you're doing tangent, what does the graph of tangent look like? Like sine is like that, like -1 to 1. That's not a great picture, but between -1 to 1, what's tangent look like? Who remembers?
Be between positive and negative infinity.
Yeah, it goes positive, negative infinity. So it's doing this. So there's no restriction. But when do you use tangent? Not when it's minus. When do you use it? When it's addition. And so there would be no negatives under the square root because you're adding 2 perfect squares. So there should not be a restriction here, and there's not one. And so secant, it turns out, works the same way. It's like when you have like x squared minus 16, you'd use secant. Well, in those cases, x has to be bigger than 4 or smaller than -4. Well, secant's graph looks like this, if you remember from trig, where like it's between, it ignores the part, or it doesn't have the values where sine and cosine are. So it's like from 1 up and -1 down. And so those correspond perfectly with the square roots we're trying to get rid of. And so when they figured this out, that was a really good move, because it does line up the way we need it to for these square roots to work. Does that make sense to everybody? Okay, the other thing that's a problem is that sine repeats itself all the time. So like it's periodic, meaning it goes up and down forever, and it hits these values not just once. X doesn't do that. So when you're talking about a square root function, X doesn't repeat itself or anything like that. And so there's an implied assumption on this problem that we're not stating, and we probably should have stated it. So I'm going to write it in blue because this is something we are using. So when we're making this substitution, it's understood that for sine, theta is between negative pi over 2 and pi over 2. Though there's a similar restriction for tangent and a similar restriction for secant. And if you go look at the textbook, it will show you what those are. But that makes it so that you only cover the range of sine once. So like if you're looking at the graph of sine, it goes from 1 to -1 exactly once when we talk about pi over 2 to negative pi over 2. And so it covers the entire range and it hits it only one time. Similar for tangent and secant. Those domain restrictions that we use, those are the same. They cover the whole range and they cover it one time. Tangents is negative pi over 2 to pi over 2. Secants varies from textbook to textbook, but it works for what we need. All right, so that means we're okay here. Okay, so this one is good. Now, the next spot we cheat is down here where we're taking the absolute value. So when is it okay not to put an absolute value? So we said the other day, square root of x squared is not usually x, or not always x, but when is it x? When is this true? This is not always true. If it's, is that true? Go ahead, Andy.
Is it what, when it's positive? Or?
When it's positive. Yeah, so if x is positive, the square root of x squared is just x. If x is negative, it's not. And so the idea here is it turns out we know cosine is positive. How do we know that? Is cosine always positive? It's not. But on this restriction, it is. Does that make sense? So pi over 2 to negative pi over 2, those are angles in the first and fourth quadrants. In those two quadrants, cosine is positive. So this is okay to not have the absolute value because on the restriction that we chose, cosine does have to be positive. Sine doesn't, but when we get to this cosine, it does. So it's okay not to have the absolute value because we know it's positive. Even though we've never said that, that's been true the whole time. Does that make sense? Okay. Back over to the picture. So here we cheat. We're assuming theta here is not from negative pi over 2 to pi over 2, but theta is between 0 and pi over 2. That may not be the case. And so what happens is the diagram really could look like this. So it's possible that theta is there. If that's the case, so we're talking about negative pi over 2 to pi over 2. If that's the case, then we would label the triangle x here and 3 here. And we would not put negative x. Why would we not put negative x even though that's clearly a negative y value? Why would we not do that? Because x itself would be negative. The variable x would be negative in this case. Does that make sense? Okay, so if it's in the fourth quadrant, the labels there are the same. When we use the Pythagorean theorem, the labels are the same. And so it turns out that when we're drawing this picture, it actually could be this picture, but all of the sides are labeled the same. So when we're using it to get these answers, we're gonna get the same thing because the opposite side, the adjacent side, the hypotenuse side, those are all the same as they are here. So yes, this is a possibility instead, but it doesn't matter because when we're doing it here, we get the same stuff. So we do gloss over that, but it's okay because it won't change any of our answers. Does that make sense to everybody? Clear? All right, last spot. So this is okay last spot is here where we're saying, okay, theta is the inverse sine of x over 3. So what we have said the past couple days is that when we're doing this, you must use this original function. The reason for that is because the domain restriction that corresponds to that is the same one as for inverse sine. It's not the same as for inverse cosine. It's not the same as for inverse secant. This corresponds to this domain restriction, which means this is right. But if you were to put inverse cosine of square root 9 minus x squared over 3, which it looks like you could do, you would be wrong because the domain restriction for cosine is different from the domain restriction for sine. So these restrictions that we're using for sine, tangent, and secant correspond to their inverse functions, meaning that doing this is okay as long as we're using the trig function that we started with. Now, that past 5-10 minute discussion seems like an hour and a half probably. That discussion is why everything we've done for the past 2.5 lectures is allowed. Okay, it's important why it's allowed, but we have done all of the examples without ever having discussed that theory. So even though that theory is important, when you're doing the problems, it doesn't affect what you are doing. Does that make sense? Everybody understand that? So yes, I would like you to understand that. Is it vital that you understand it in order to be able to do the problems? No. Clear? Okay, questions on this? Everybody's good? Okay, I want to give you a heads up of what's coming up and talk about the homework for trig sub. So, and talk for a minute about exam 2. So, okay, exam 2 is next Thursday. What's the date on that? Is it October 8th? Is that right? I think October 8th. Let me double check the calendar so I'm not putting a video that is wrong. All right, yeah.
It's right.
Yeah, 10-8. Okay, so exam 2 is next Thursday, 10-8. The topics on exam 2 will include average value and arc length. We're talking minor coverage on those, at most 2 questions. So maybe 1 average value, maybe 1 arc length. What might even be more likely is that half of you will get average value and half of you will get arc length, and it'll pick it at random. Does that make sense? I don't know for sure. I haven't designed the test yet, but at most 1 of each, maybe not any. Okay, so at most 1 of each. Then integrals is the biggest part. Whoops, no M in integrals. And that's mostly unit 1, or that is unit 1. Man, I'm struggling. Unit 1. Okay, that includes U sub. Not that that's new for this test, but there will be problems mixed in where you're obviously using U sub. That includes parts. That includes trig integrals, which that's not trig substitution. That's like powers of sine and cosine, powers of secant and tangent, and then cosecant and cotangent. So like those problems we were doing before trig sub, so like Monday and the end of last week. And then it includes trig substitution, which is what we've now been talking about for the past 2 days, or 2.5 days, 3 days now. And that includes partial fractions, which is what we will start talking about tomorrow. And then Monday, Tuesday of next week. Okay, so that will take us through the test. It will include that. If you have seen a schedule, I don't think I put the schedule up in your all's thing on purpose, because I'd rather kind of keep it where we need to be, not necessarily follow the schedule exactly. But if you do see a schedule somewhere that says improper integrals will not be on exam 2, Okay, so we'll deal with that later. But these are the topics for exam 2. For trig sub, obviously these problems take a while, okay? And they definitely take some practice. And so when you do that on Webassign, there's maybe not quite as many problems as what we would normally have. So I think Webassign, I think I put 8 problems, which is actually quite a bit still, but it's probably not enough to be really comfortable with trig sub. So you need to do the worksheets, the worksheet in the Unit 1 folder. And it's folder, let me double check. I think it's folder 6. Yeah, folder 6. And you have in there, you have 3 files. One file is, whoops, that's integration by parts. There are 3 files in there. One file just says trig substitution. That's the set of practice problems. Then the second file is solutions to that. And then there's a third one, which I'm not going to require, that's trig sub homework. It just has 4 problems that I normally assign as written homework, but you have the Webassign, and I think that's enough for required assignments. So the Webassign is due Monday, like every other homework assignment for this week. But we're done talking about trig sub now. So you do need to get comfortable with trig sub. Remember, your test is open book, open note, but as you found out last time, you don't have a lot of time. Like I think you'll have enough time to do the test, but you're not going to have a ton of time to like look up example problems. So you're going to need to get organized with the formulas, and you should make a formula sheet. And if you want me to help you kind of organize your notes, I can try to do that over Zoom, but you definitely want to get it organized for this, because you're not going to have time probably to sort through pages and pages of examples. You're welcome to do that. The problem is you're going to have to, the time will be better on this exam than it was on the last exam, but you do need to work fairly quickly. Does that make sense? All right. So anyway, so that's the trig sub stuff. Partial fractions, that'll start tomorrow. Chances are you won't have homework that I'll collect because it'll be test week next week. So this Webassign will be the last required assignment. I will have a couple of worksheets for partial fractions. I'll probably put a partial fractions Webassign up, but I'll probably make it optional. I might make it bonus. We'll talk about that maybe tomorrow or early next week. But you'll need to make sure you've done the homework, but I'll let you pace that how you want since it's test week. But that'll take us through the exam. We'll start with the basics of partial fractions tomorrow. We'll do more with that Monday, Tuesday. We won't have a lecture this Friday, but I can be available if you want to meet up and go over problems. You just need to let me know. But I'm happy to meet up on Friday at 12:30 if you want. Okay, I think that's it for today. Thanks for coming. If you have questions, stick around. And if not, I will see you guys tomorrow. Thanks, you guys.